students, welcome back to 60 out of 60 in KCET Chemistry 2025 examination in just 200 days. So today we are going to start a new chapter, that is equilibrium. Okay, you know equilibrium has two parts, chemical equilibrium and ionic equilibrium. So today we are going to discuss about chemical equilibrium. Okay, and we'll be doing some basic introduction, and then we'll be discussing about equilibrium in physical and chemical processes, and then we will discuss about equilibrium constant. Okay, so students, please join our WhatsApp channel, link is there in the description section. This will help you to get access to our PDF notes, mock test and solutions. Okay, so now please sit with the notebook. This chapter is very easy, especially the chemical equilibrium part, and in your board exam, in your KCET examination also, mostly questions are asked from the chemical equilibrium part, which is highly scoring. Okay, so please watch this complete video. I'll be telling you all the type of questions that can be asked. We are going to discuss a lot like important questions, and we will be completing the introduction part today in a comprehensive way. Okay, so let's get started here. First one, if you see, we will be doing this chapter in 4 parts. Okay, so in today's class, that is in part 1, we are going to discuss equilibrium in physical process, equilibrium in chemical process and law of chemical equilibrium. Clear? And in the second lecture, we are going to discuss homogeneous equilibrium, heterogeneous equilibrium, applications of Kc and relationship between K, Q and G. Next, in part 3, we will be discussing factors affecting equilibria. Ionic equilibrium will be starting, then acids, bases and salts, ionization of acids and bases, and in the last lecture we will be doing buffer solution and solubility product. Okay, so going to be a very big chapter, but do not worry, I will be teaching you in a very simple way so that you can solve all the questions being asked from this particular chapter. Fine. Now coming to year wise weightage, you can see this is like, if you consider PU1 topics, they generally have low weightage in your KCET examination, but chemical bonding and chemical equilibrium are the two topics from PU1 which are also very important for your KCET examination. So make sure that you can see almost two questions are being asked for the last 4-5 years, and 2024 there was one question from solubility product, and then in 2019, 18 and 17 also you can expect like one question was asked. Okay, so definitely you can expect 1 to 2 questions from this chapter. Okay, and they are very easy if you do this particular lecture. 4 lectures if you complete, I'll keep them very short and crisp and to the point so that you can just watch it and complete this chapter in a very short time. Fine. Now coming to today, we are going to discuss introduction. I'll be telling you what exactly is equilibrium, what does it mean, then physical equilibrium and law of chemical equilibrium. So in physical equilibrium, we'll be seeing solid liquid equilibrium, liquid vapor equilibrium, solid vapor equilibrium, dissolution of solid in liquid, dissolution of gas in liquid. Okay, next coming to the first thing, what is equilibrium? Okay, so now see, equilibrium exists when two different processes occur at the same rate. Two opposite process occurs at the same rate. Okay, when can you find equilibrium? Equilibrium is obtained, or equilibrium can be observed when two different processes, two opposite processes occur at the same rate. You might not have understood anything. I'll give you a very simple example and we'll understand. Now, what is the consequence of this one? So, due to this two opposite process occurring at the same rate, concentration remains constant. Okay, this is the consequence of this one. So, this is what is equilibrium. How can we define? Equilibrium is obtained when two opposite processes occurs at the same rate and the concentration remains constant. Let us see a very simple example. Suppose you have a tank of water. Okay, you have a tank of water, and here you have one opening and here you have one opening. Okay, now what happens? In this tank of water you have 5 molecules of water. Okay, there are 5 molecules of water. Now what happens here? Okay, this is from where? This is water inlet, means water can enter from this side, and this one is outlet. Okay, water can go out from this side. Now what happens? Suppose, just imagine that, okay, now 1 drop of water comes inside. Okay, so what is the role of this one? It will increase the level of water. Increase the level of water. right? This will increase the level of water. Now from here, suppose one drop is going out. What is the role of this one? decrease the level of water. Okay, so if one water is added, one molecule of water is added, the level of water here will increase, and if here one water is lost, then the water level will decrease. So these are two opposite processes. Now see, suppose one water is added, okay, and at the same time one water goes out. When this one is added, it became 6, right? When one loses or one of them is lost, it again becomes 5, right? So when you add 1, it is becoming 6, then again it is losing, it again remains 5. Next you added 1 and more, okay, sorry, you added 1 more, it became now again 6, and again there is a loss of 1, and that is why we get again 5, right? So now here one water molecule is added, one water molecule is added, one water molecule is removed, right? So that is called as balancing, or that is called as the rate of two opposite processes. What is the opposite processes? Filling of water can and removal of water from the can, okay, or emptying the water tank, right? These two processes are occurring at the same rate. Now what is the meaning if they are not occurring at the same rate? Suppose two water molecules are added. See, we have these 5 molecules of water at the I'll erase everything. Now see, 1 second, okay, fine. So now suppose we have 5 molecules of water as we started, okay, and then the number of molecules entering is 2, okay, and the number of outlets that can go out is 1. So now suppose this 2 molecule entered, so it was 5, now it became 7, right? Now 1 molecule will go out, right? So it will become now 1, 2, 3, 4, 5, 6. Okay. So now because the rate are not same, because 2 entering, 1 leaving, the rate is not same, so the concentration will not remain constant. The concentration changed. Earlier it was 5 molecules, now it became 6 molecules, right? So the concentration will remain constant if the rate of two opposite processes are equal. Okay, one molecule coming out means one molecule should go out. Okay, that is called as equilibrium, and the concentration is not exactly constant. See, these 5 molecules are not same. Suppose I tag them as one, see, suppose I name them. This is A, this is B, this is C, this is D. Okay, now what will happen? This is E and this is F. So now new molecules are added and the old molecules are going out. Okay, the molecules are changing, but it appears to be constant because the two rates are opposite to each other. Clear? Now we will talk about physical equilibrium. So physical equilibrium means that includes physical processes. Equilibrium in physical process. Okay, like first physical equilibrium example is solid liquid equilibrium. Now what is meaning of solid liquid equilibrium? The solid and the liquid phases are at equilibrium. Okay, now example here is ice and water. We give equilibrium sign with a double arrow. Okay, now ice and water. Now number of molecules getting converted to water should be equal to number of molecules converted to ice. Okay, like for example, so now this temperature, okay, at which the equilibrium is there between ice and water is called as your melting point. Okay, the temperature at which there is equilibrium between the ice and the water phase, or the liquid and the solid phase of a compound, is called as its melting point. Okay, now the same thing appears. The number, suppose 2 molecules of ice are converting into water, 2 molecules of water should should freeze to give you ice. Okay, then what is the process here? Now here the freezing rate should be equal to melting rate. Okay, two opposite process should be equal. If 2 molecules of water are melting, 2 molecules of ice are melting to give you water, 2 molecules of water should freeze to give you ice, and then both the water and ice concentration will remain constant. Next one is your liquid and vapor equilibrium. Now this one is existing the phase, like the temperature at which there is an equilibrium between liquid and vapor, that is called as normal boiling point. Okay, so normal boiling point is the temperature where the liquid and the vapor phases are at equilibrium. Then here also you can take the example of water, liquid, and water, gas. Okay, so number of molecules evaporating to gas, number of gas molecules condensing to water should be equal. Okay, Now depends on the atmospheric pressure and altitude of the place. Depends on the atmospheric pressure and altitude of the place. Okay, boiling point is never constant, it is always dependent on the pressure and temperature. That is why you can see at the higher altitude the boiling point is less, right? So boiling point becomes less because the pressure is less. Clear? Fine. Next, coming to the third one, solid vapor equilibrium. It is also similar to this. Solid and vapor phases will be at equilibrium. Example, you can take water at the gas and water at ice. Okay, or you can say iodine gas and iodine solid. Okay, now iodine is something which is sublime, which is a substance that can sublime, right? So now because this can undergo sublime, so when iodine gets converted to vapor, it creates vapors. Okay, you can see dense color vapors, but after some time the intensity of the vapor remains constant. That is because it has attained equilibrium. Okay, so these are the examples of physical equilibrium. Now there is one more type of physical equilibrium, that is dissolution. Okay, dissolution of solid in liquid. Okay, when you are dissolving any solid in liquid, so there also there is an equilibrium established, number of particles getting dissolved, number of particles coming out from the solution. Okay, that is also an equilibrium established, and the dissolution of gas in liquid. Okay, so that is also one equilibrium established here. Now coming to chemical equilibrium, this is from where questions will be asked in the examination, the most important part. Now see, suppose I have a chemical reaction AA plus BB, okay, gives you CC plus DD. Okay, now this is forward reaction and this is backward reaction, right? Now the forward or the backward reaction always depend on the rate of forward reaction and the rate of backward reaction, or any rate is always dependent on the concentration of the reactants. What I am saying here, rate is, right, dependent on concentration of reactants. Okay, so now if I write rate of forward reaction, okay, that is proportional to what? This is forward reaction, it is proportional to concentration of A and concentration of B, right? So I can say it is A to the power of A and B to the power of B. Okay, rate is proportional to the concentration of the reactants raised to the power of their stoichiometric, raised to the power of their stoichiometric coefficients. Okay, this is called as law of active masses. Okay, you just need to know this. So I can write the rate of forward reaction is proportional to concentration of A to the power of A, concentration of B to the power of B. Now for the backward reaction, this is what? For the backward reaction, these are the reactants. So I can write that rate of backward reaction, okay, is proportional to C to the power of C and D to the power of D. Okay, now to remove this proportionality, we can just multiply a constant. RF is equal to KF. So this is called as rate constant or forward reaction to the power A to the power of A and B to the power of B. And RB is equal to KB into C to the power of C and D to the power of D, right? Now we know that at equilibrium the forward reaction is equal to the backward reaction, right? So at equilibrium what we can say, that forward reaction is equal to backward reaction. That means I can say this one is equal to this one. So I can write KF into A to the power of A and B to the power of B is equal to KB into C to the power of C and D to the power of D. Okay, now the rate constant, the equilibrium constant, if I write a reaction, that will be KF by KB. Just I'll take this equation, KF by KB will be equal to C to the power of C, D to the power of D and B to the power of B and A to the power of A, right? So this equation is called as your equilibrium constant. Okay, K equilibrium or equilibrium constant. What does tell? What does equilibrium constant tells you? It gives you the ratio of the product's concentration divided by the reactant concentration raised to the power of their stoichiometric coefficients. And remember here, once this K equilibrium we can calculate once the reaction has attained equilibrium. Once the reaction has attained equilibrium. Okay. So initially you cannot calculate. Once the reaction has proceeded and it has attained equilibrium, after that you can calculate the equilibrium constant. And which concentrations that you are taking, right? This concentration of C, concentration of D, right? Concentration of A and concentration of B. These all are what? The concentrations at equilibrium. When the reaction has already reached equilibrium, at that time what all are the concentrations of A, B, C, D, that is what is there. Okay. Now remember, we have discussed that the concentration should not change at equilibrium, but that doesn't mean that the concentration is same. Okay, concentration being same, concentration is not changing are two different things. Now see, means what I want to say, that the concentration of A, B, C, D can be anything. It can be X, it can be Y, it can be A, like P or Q. Okay, so this can be P or Q. Okay, all the concentrations can be different. A concentration is different, B concentration is different, C, D concentrations are different. But once the reaction has reached equilibrium, also their concentrations can be different. But once the reaction has reached equilibrium, A concentration will be X only for the next certain period of time. B concentration will be Y for the certain period of time till the equilibrium is not changed. Right. So once the reaction has attained equilibrium, at equilibrium whatever is the concentration, that will continue for a certain period of time. Okay. So that is what is the meaning of concentration remains constant. Many students think that concentration will be equal. No, concentration is not equal. Concentration remains constant for a certain period of time. Okay. Now what something we should know about this equilibrium constant K. Okay, so equilibrium constant A, okay, it is independent of, first point, it is independent of initial concentration. Means how much A you take, how much B you took, C you took, D you took, that is not at all affecting the K value. When the reaction has reached equilibrium, at that time what are the concentrations A, B, C, D, that is what K equilibrium is worried about. Okay, or is concerned about the concentrations of the reactants and products at equilibrium. Once the reaction has reached equilibrium, what are the concentrations of A, B, C, D, that is used to calculate the equilibrium constant. Okay, next, it is not affected by not affected by catalyst. Not affected by catalyst. Now what is the meaning of this? Suppose you have done this reaction, AB gives you C plus D, and the reaction has proceeded, and after 15 minutes, okay, after 15 minutes the reaction attained equilibrium and the concentrations are X, Y, P and Q at equilibrium. Okay, after 15 minutes this reaction happened. Now if you use a catalyst, okay, then the reaction will attain equilibrium in 5 minutes. Okay, but the concentration still will be X, Y, P and Q. Okay, these concentrations will not change even if you use a catalyst. So what does the catalyst will do? The catalyst will help you to reach equilibrium in a shorter period of time. If you are without catalyst, if you are reaching the equilibrium in 15 minutes, with catalyst you will reach equilibrium in 10 minutes or 5 minutes or less than that, right? So that is an example. So the point here is the concentrations which will be at equilibrium, that will happen even if you use catalyst or do not use catalyst. So if concentrations are not changing, K value will also be not changing, right? So these are the things about equilibrium constant that you should know, and the formula of equilibrium constant here I have written. That is very, very important. Okay, product concentration by reactant concentration. Okay, so now we will practice some questions based on what we have studied till now. Now let us see the first question. The value of equilibrium constant for different chemical reactions at a particular temperature is. Okay, now if you, the question is saying that we have reaction 1, okay, where A plus B is giving you C plus D. we are having one more reaction where X plus Y, okay, is giving P plus Q. Both these reactions are occurring at 273 Kelvin. Okay, then the question is asking that whether these equilibrium constants of two different reactions at the same temperature will be. So now the value of equilibrium constant for one particular reaction is the same value. Okay, so that is why it is unique. Okay, for every different reactions the rate of the equilibrium constant will be unique. For this reaction if it is K1, for this reaction it will be K2. Okay. Okay, next is question number 2. What does it indicate having a higher equilibrium constant? Okay, so now suppose you have a reaction A plus B, okay, giving you C plus D, okay, and you have one more reaction P plus Q is giving you X plus Y. This value is K1 and this value is K2, and K1 is greater than K2, right? Then what can you say about the reaction? Now see, what will be the expression for K1? K1 is concentration of C into concentration of D divided by concentration of A divided by concentration of B. Now K2 value will be concentration of X, concentration of Y divided by concentration of P and concentration of Q, right? Now what happens? Now see, if K1 value is high, that means this numerator is high, C and D concentrations will be very high. If C and D is concentrations are high, that means what? Reaction is more favored towards the products. Okay, products formation is more what I can say is the reaction is more favored towards the product formation. So what we can see here, reaction occurs faster and gives you C plus D immediately, and that is why this numerator is more, and that is why K1 value will be more. Rate of backward reaction is faster? No. If rate of backward reaction is faster, then A plus B concentration will be more, right? But that is not the case. Both backward and reaction rates are equal? No. Reaction may be slower than usual? No. Correct answer is option number A here. Next question number 3, if the initial concentration of reactants in a reaction increase, then the equilibrium constant. So we have discussed that the equilibrium constant is independent of the initial concentration. It doesn't depend on the initial concentration, right? So that is why it still will remain constant. Okay, that means suppose you have a reaction A plus B giving you C plus D. Okay, and you started this with 1 mole of A and 1 mole of B, and after 15 minutes, okay, the reaction is now at equilibrium. Okay, and we don't have this equilibrium sign now because now the reaction is not at equilibrium. We have just started, and at equilibrium this is 0.2 and 0.2. Clear? Now what I did is I did the same reaction with, and okay, one second. We did, okay, now in this case K1 I found the value of equilibrium constant is K1. Now I did the same reaction, but I started with 1.2 mole of A and 1.2 mole of B. At equilibrium again it is 0.2 and 0.2. So again this for this reaction also the equilibrium constant will be K1. So it is not dependent on the initial concentration of A and B, right? It is dependent on the concentration of A and B that you have taken at that time. Okay, so the concentration remains constant, equilibrium constant remains constant. Okay, question number 4 here, what is the equilibrium constant for the following reaction? So you have been given with 4NH3, okay, plus 5O2 and gives you 4NO plus 6H2O. Okay, now if I want to calculate K equilibrium for this one, so it will be product concentration. So product is NO to the power of 4, then I have another product that is 6H2O to the power of 6, then I have NH3 to the power of 4 and O2 to the power of 5. Okay, so now you can see what will be the correct option here, NO to the power of 4, H2 to the power of 6, NH3 to the power of 4, O2 to the power of 5, that is option number D here. Okay. Next, coming to question number 5 here, given that at 800 Kelvin that concentrations are as follows. Okay, so concentration let us note down first. N2 concentration is 3 into 10 to the power of minus 3. Okay, O2 is 4.2 into 10 to the power of minus 3. Okay. Next we have NO as 2.8 into 10 to the power of minus 3. Okay. What is the equilibrium constant for the reaction? So the reaction is N2O2 gives you 2NO. So first let us write the value of K equilibrium. So that is NO concentration to the power of 2 divided by N2 concentration divided by O2 concentration. So now if I substitute here the values, so it is 2.8 into 10 to the power of minus 3 whole square divided by N2 is 3 into 10 to the power of minus 3 divide into 4.2 into 10 to the power of minus 3. Okay. So now if you solve this, we will get 2.8 divided by 3 into 4.2. Okay. Now if I solve this, we will be getting around 0.622. So correct answer is option number A here. Okay. So now one more question. Select the correct equilibrium using physical equilibrium. Okay. It is possible only in a closed system at a given temperature. Okay. So now whether this statement is correct or not, let us understand this. Suppose let us consider about liquid vapor equilibrium. Okay. So liquid vapor equilibrium means what? Now see, suppose I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules of liquid water. Okay. Now vaporization is taking place. One molecule went to the vapor phase. Okay. So now what I will get? So now there is one molecule in the vapor phase. Another molecule went to the vapor phase. Okay. So I will do another molecule went to the vapor phase. Okay. Now what happened? One more molecule went to the vapor phase. So we will get 3 molecules in the vapor phase, right? So after this what happened? Equilibrium attained. Okay. Now after this I can say that the equilibrium was attained after this. Now what I can say now here, so if I draw a small, one second, okay. Now see, what is the number of molecules in the water phase? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8 molecules are in the water phase and 3 molecules are in the vapor phase. Okay, and after this suppose equilibrium is attained. Now what do you mean by that the equilibrium is attained now? Now if one molecule goes to the water phase, okay, sorry, one molecule goes to the vapor phase, at the same time one molecule should come back to the liquid phase. Means what? Here evaporation, rate of evaporation, right, should be equal to rate of condensation. Right. Now suppose this molecule went to the vapor phase, right? So that means what? This molecule went to the vapor phase and this molecule will come back to the liquid phase. Okay. So, okay. So now you can see again we have 3 molecules in the vapor phase and 8 molecules in the 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So again we have the same number of molecules in the vapor phase as well, right? So that is called as equilibrium is attained. Now suppose the lid is closed. Okay. Now suppose the lid is open. Okay. So these molecules which were there in the vapor phase will escape, right? And after that we will never attain the equilibrium. So for the equilibrium to attain, this lid or this container should be a closed container. Okay. So that is why this statement is correct. Next, both forward and backward does not occur at the same rate. No, I told you for the equilibrium to be attained, both the opposite processes should be at the same rate. Next, there is a dynamic but an unstable condition. No, it is a stable condition. Okay, measurable properties of the system do not remain constant. They also remain constant. So the correct statement is option number A here. Okay. Fine. Now this is a homework question. Which of the following is an example of solid liquid equilibrium? So water and steam at 100 degrees centigrade, water and ice at 0 degrees centigrade, the point where ammonia is sublimized, boiling point of water. Okay, just you have to answer, very simple question. So please put down the answer in the comment section, and in the next class we are going to solve a lot of numericals and we will be discussing some most important terms. So please stay tuned for next class and do not forget to subscribe the channel if you are liking this video. Thank you for watching and see you soon in the next class.